So today I'm going to cover main algebraic topics required in AMC8. It consists of 3 parts. The first part is number theory, and the second part is counting problems. Lastly, I will talk probability. Probability partially depends on number theory and counting problems. So in number theory, there are divisibility test problems, prime numbers, and prime factorization problems, and the Lcm, which is least common multiple, Gcd, greatest common divisor, and the remainder problems. The second part, counting problems, we start from multiplication principle and the permutation, combination, inclusion, exclusion principle, and also some techniques like binding and insertion. So let me start from the number theory. So the first question on number theory is on divisibility test. Number theory studies integer numbers or whole numbers. The very basic relation is that one number is divisible by the other. Here, let's consider general number here. Capital N is a big number, a lot of digits. There are n digits here. We consider the divisibility test for 2, 3, 4, 5, 8, 9, and 11. Basically, if n is divisible by 2, by this number, how to describe that? First, if n is divisible by 2, basically it means it's even number. It's easy to tell. We just look at the last digit. If the last digit is even, the original number is even. For example, 2021, the last digit is not even, so this is not divisible by 2. But 2022, the last digit is 2, so this number is divisible by 2. That's divisibility test for 2, very easy. And next, we consider divisibility test for 3. So in order to see if it's divisible by 3, we just look at the sum of digits. For a very big number, we consider sum of digits. For example, let me just take not too big number, 2020. Here, 2020, there are 4 digits. The sum of digits is 4. 4 is not divisible by 3, so 2020 is not divisible by 3. Instead, if you consider 2022, this number is divisible by 3 because 2 plus 2 plus 2, that's 6, divisible by 3. And next, we consider divisibility test for 4. Here, we only check the last 2 digits. If the last 2 digits make a 2-digit number divisible by 4, the original number will be divisible by 4. For example, 2020 is divisible by 4 because 20 is divisible by 4. Okay. And the 2022 is not divisible by 4 because 22 is not divisible by 4. All right. Next, we consider divisibility test for 5. A number is divisible by 5. We only look at the last digit. If it's 0 or 5, the number is divisible by 5. Easy to see 2020 is divisible by 5. 125 is divisible by 5 because the last digit is 0 or 5. But like 2136, this is not divisible by 5 because the last digit is not 0 or 5, it's 6. Okay. Next, we consider divisibility test for 8. To consider 8, we just check the last 3 digits. If the last 3 digits, this 3-digit number is divisible by 8, the original number will be divisible by 8. For example, we can have 296. I got 296 divisible by 8. It's not hard to check. Then we can imply that any number with last 3 digits 296 divisible by 8. For example, I have a 76296. This 7 and 6 doesn't matter. We just check the last 3 digits 296 is divisible by 8. So the big number is also divisible by 8. If you look at 134, this is not divisible by 8. That implies any number end with 134 not divisible by 8. For example, 946134. This is not divisible by 8. Next, we look at 9. The numbers divisible by 9. It's very similar to the numbers divisible by 3. We'll also consider the sum of digits. The sum of digits. If the sum of digits is divisible by 9, the original big number will be divisible by 9. For example, I have 1 plus 7 plus 9 plus 2 plus 8. This is 27. 27 is divisible by 9. So the number consists of these digits will be divisible by 9. 1, 7, 9, 2, 8. This big number is divisible by 9. Okay, that's divisibility test for 9. Finally, let me mention another one maybe you're not so familiar with. It is divisibility test for 11. A big number is divisible by 11. We consider something called alternating sum. Alternating sum. So recall that divisibility test for 3 and for 9, we just take the digital sum. We just add all those digits and see if it's divisible by 3 or divisible by 9. Divisibility test for 11, we consider the sum, but we change the sign. Okay, we start from A1 minus A2 plus A3 minus A4 plus A5 and so on up to the beginning digit. Okay, the sign alternates, so we call it alternating sum. Okay, so let me give you example. For example, we have 4 minus 1 plus 8. You know, this is equal to 11. It's a multiple of 11. So that implies the number 814 is divisible by 11. Also, we can take a longer number, 4-digit number, like 9 minus 4 plus 7 minus 1. This is also 11. So that means the number 1749 is divisible by 11. And it applies to longer number. You can test by yourself. Okay, those are divisibility tests frequently used in AMC8, not in AMC8, but also in AMC 10, 12, and like Amy. So you are required to know all of this. Now, based on that, let me give you some examples on some AMC8-like questions. The first example, we are given a long number, capital N, 1, 2, 3, 4, 5, 6, 7, 8, 9, and with A, B. Okay, this number is divisible by 99. The question is to find A plus B. Okay. All right, we don't have divisibility test for 99, but we have divisibility test for 9 and 11. Notice that 99 equals 9 times 11. So the original number N is divisible by 99. It implies this number is divisible by both 9 and 11. Okay, so we can use the divisibility test for 9 and for 11 to figure out the values of A and B and any properties related to that. So let's do 9 first. N is divisible by 9 implies the sum of digits is divisible by 9. The sum of digits is 1 plus 2 plus 3 up to 9 and plus A plus B. It equals, okay, 45 plus A plus B. This number is divisible by 9. And we notice that 45 is a multiple of 9. So we can ignore that part. So that implies A plus B is divisible by 9. Right? That's a conclusion from the divisibility test for 9. Now A plus B, recall that A and B are 2 digits. So A and B can only be from 0 to 9. The least number is 0, the largest number is 9. So A plus B cannot be too small, cannot be too big. A plus B is between 0 and at most 18, right? 18, 9 plus 9. So A plus B is divisible by 9. There are only 3 possibilities. It could be 0 or 9 or 18. If it's 0, then we have both number equals 0. If it's 18, we have both number equals 9. But if it's 9, there are different choices. Okay, now we start to use divisibility test for 11. This number is divisible by 11. That implies the alternating sum is divisible by 11. The alternating sum is B minus A plus 9 minus A plus 7 minus 6 plus 5 minus 4 plus 3 minus 2 plus 1. And it's not hard to see this equals B minus A plus 5. So B minus A plus 5 is a multiple of 11. Let's see, B minus A plus 5. Okay, B minus A is B is at least 0, A is at most 9, so B minus A is at least minus 9. B minus A is at most minus 9, at least minus 9 and at most 9. Plus 5, EV plus 5. That means this number is at least minus 4 and at most 14 is divisible by 11. That means B minus A plus 5 could be 0 or 11. There are two choices, right? And so accordingly, we have B minus A, we subtract 5 equals minus 5 or 6. So B minus A equals minus 5 or 6. Right, let's combine two parts and to figure out A and B. So the first part says that A plus B equals 0 or 9 or 18. And we can easily exclude 0 and 18. So if A plus B equals 0, that means A and B are both 0. That's definitely invalid because you can check the second part. B minus A should be minus 5 or 6. That doesn't work. So, and if A plus B equals 18, that means A and B are both 9. Also invalid because B minus A should be minus 5 or 6. Now, we only have the last case. It is A plus B equals 9. And we have B minus A equals minus 5 or 6. And actually, we can easily see it should be minus 5. It cannot be 6 because A plus B, B minus A and B plus A, these two terms must have the same parity. Should be both odd or both even. Because you see their difference 2A is even number. Their difference is even number. B plus A minus B minus A is 2A, which is even. So they must share the same parity, both odd or both even. Now, A plus B equals 9, so B minus A also should be odd, so minus 5. So actually we can conclude A plus B and 9. And moreover, we can solve A and B explicitly. We can do more than the question asked. So A equals 7 and B equals 2. And you can answer any question related to A and B. Okay, that's an example, okay, related to the divisibility test. Next, let me talk about the prime numbers and the prime factorization. An important element in number theory is prime number. A prime number is a number that is greater than 1 that has only 2 factors. The number is itself and 1. So here are a list of prime numbers, 2, 3, 5, 7, 11, 13, 17, and so on. There are infinitely many prime numbers. And here I'm going to highlight this 2. This 2 is the only even prime number. Only even prime number. For all other prime numbers, they are odd. So sometimes AMC8 tests such property. Here, let me give you a simple example, very quick. So there are 3 prime numbers, PQR. P plus Q equals 55. Q plus R equals 99. What is R plus P? Right. So here, the point is to check the parity. If they are all odd primes, the sum will be even. But here, we have both sum to be odd. 55 odd, 99 odd. So there must be one prime number in each equation that is 2. So 55 should be equal to 2 plus 53. 99 must be 97 plus 2. We must have 2 there, so we can figure out the other number. And we see that Q appears in both equations, so Q should be this 2. And accordingly, R is 97, P is 53. Easily, we can solve R plus P equals 97 plus 53, which is 150. Okay. So the point is that 2 is the only even prime number. That's the key. So next, let me mention the prime factorization. If a number is not prime, it can be factored into the product of many prime numbers. So this is called a fundamental theorem of arithmetic. Every integer greater than 1 is either a prime itself, or it can be represented as the product of prime numbers, like the following. So n equals p1, maybe repeated k1 times, p2 repeated k2 times, pm km times. Here, P1, P2, Pm are distinct prime numbers. And this K1, K2, they are integer, they are positive integers. And this factorization is unique if the order is not important. For example, we can have a 360. I can divide it by prime number is divided by 2, and then 4. Okay, I can factor this into 2 cubed times 3 squared times 5. So this is a prime factorization of 360. So there are a lot of important and very useful properties based on prime factorization. Let me mention a couple of them. The first one, we can use prime factorization to characterize a square number. A number n is a perfect square. We only look at the exponents. All exponents are even. The number is a square number. The exponents are k1, k2 up to kn. So example is like I have a 2 to the 4th power times 3 squared times 5 to the 6th power. Okay, here the exponents are 2 and 4, 2, and 6. They are all even. So this can be written as a square because 2 squared times 3 times 5 cubed and the whole product square, which is double the exponent. So that's why we require every exponent to be even to characterize this perfect square. Instead, if we have 2 cubed times 3/4, this is not a perfect square because the exponent for 2 is 3. That's odd number, which is not even. So not good. Similarly, we can describe a number is a cubic number. A number is a cubic number if and only if those exponents k1, k2 up to km, they are divisible by 3. They are divisible by 3. Let me write one example: 2 cubed times 3, 6 times 7, 9. Okay, here exponents are 3, 6, and 9. They are all multiples of 3. So this is a cubic number because it can be written as 2 times 3 squared, 7 cubed, and the whole product cubed. Right? That's why we require the exponent to be divisible by 3. Instead, if you have 2 squared times 3 cubed, this is not, because this 2 is not a multiple of 3. Another very important fact is the number of factors. Given a number n, how can we find the total number of factors? Here's the formula. It equals k1 plus 1 times k2 plus 2, k2 plus 1 up to kn plus 1. The reason is that for a number n, I just repeat this factorization. This is a prime factorization for n, for number n. We want to see how many factors it has. So a factor must have following format. A factor means its divisors are all from n. So D must be of this type. P1 with some exponent. Let me call it like T1. P2, T2, Tn, Tn. Those T1, T2, Tm are integers. D is a factor of n. That means this T1 is between 0 and K1. It cannot be larger than that because it's a factor of n. T2 is from 0 to K2. Similarly, Tm is from 0 to Kn. So every exponent have multiple choice. For example, T1 has K1 plus 1 choices. T2 has K2 plus 1 because it could be 0 choices. Here we also have Km plus 1 choices. So actually it's based on some counting technique called multiplication principle. So they are totally K1 plus 1, K2 plus 1, Km plus 1 factors. Each choice of T1, T2, Tm determines a factor. So there are such many factors. So this is some properties. Now let's do an example based on that and help you understand these 3 properties. The first one, let's take example like n number is 10 factorial. Okay, 10 factorial means the product of all integers from 1 up to 10. So the first question is, how many factors does n have? Direct application of the formula, right? First, we need to do prime factorization of this number. So let's rewrite 10 factorial. It is 1 times 2 times 3 times 4. Okay, 4. Let me factor 4. 4 is 2 square. And 5. And 6. Okay, 6 is 2 times 3. And 7. Okay, 7 is prime already. 8 equals 2 cube. And 9, 3 square. 10, 2 times 5. So this is 10 factorial. Let's combine like terms. So finally, you will have there are totally 8 twos. 1, 2, 3, 4. Some of there are 8 twos. And there are 4 threes. And there are 2 5s. And there's only 1 7. Okay, this is the prime factorization of this 10 factorial. Now we just apply our formula. How many factors does n have? It is just 8 plus 1 times 4 plus 1 times 2 plus 1. Okay, 7, there's only 1 7, so actually the exponent mean corresponds to 1. So times 1 plus 1, and you just multiply, you get 270. So there are 270 factors corresponds to n. Okay. Now, sometimes the question asks further numbers, like here, how many factors of n are squares? We know there are 270 factors. Some of them are squares. The question is how many of them are squares? So recall that if number is square, we only need to have its exponent, every exponent to be even, right? So if a number is a factor, it should be of the following form: is 2 to some power a, and 3 to some power b, and 5 to some power c, and 7 to some power d. Because it's from 10 factorial. 10 factorial has these 4 factors, 4 prime factors. Now, in order to be square, we need all of them to be even. A, B, C, D to be even. But on the other hand, this is the divisor. This is a factor of 10 factorial. So A should be less equal to 8. B should be less equal to 4. And C is at most 2. D is at most 1. And let's see how many choices are there. So for A, it could be 0, 2, 4, 6, 8. There are 5 choices. For B, it could be 0, 2, and 4. There are 3 choices. For C, it could be 0 and 2, right? There are 2 choices. For D, there's only 1 choice. D can only be 0. So there's only 1 choice. So the number of square factor corresponds to 5 times 3 times 2 times 1, which is 30. So our conclusion is that there are 30 factors. They are square. They are perfect square. Okay, that's the second question. First, let me test your understanding on the cubic. Okay, how to describe cubic number. What's the smallest positive integer k? So k times this 10 factorial becomes a cubic number. So we see 10 factorial itself is not a cubic number, right? Because this exponent a is not divisible by 3. But we can multiply 10 factorial by some number to be a cubic number. What's the smallest such number? Okay, let me put it here. 10 factorial times k, 2 to the 8 times 3 to the 4th times 5 squared times 7. This is 10 factorial. Now I'm going to add some k to be a cubic number. So we need to match certain 2, 3, 5, and 7 to make every exponent to be divisible by 3. So we should have a 2 to certain power, let me call it x, and 3 to certain power y, and 5 to certain power z, and 7 to certain power maybe w. Okay, now we can combine it. So we want k to be as small as possible, so we don't consider other prime factors. So we have 2, the exponent is a plus x, and 3 is 4 plus y, and 5 is 2 plus z, 7 is 1 plus w. Okay. Now every number, every exponent here should be divisible by 3, right? Let's see. The smallest number for x equals 1. For y equals 2, because 6 is divided by 3. And z, the small number should be 1, 2 plus 1, 3. And w, we need at least 2. So that's the minimum requirement for the exponent for k. So the minimum for k equals 2 times 3 square and 5 times 7 square. And you do computation 4,410. That's the minimum value of k. Right? So finally, let's do another question on this topic. So how many factors have at most 3 factors? Okay, how many factors of 10 factorial have at most 3 factors? We know 10 factorial is 2 to the 8 times 3 to the 4th power and 5 square times 7, right? There are 270 factors. How many factors of them have at most 3 factors? Right, we can just do case what we discussed. If there's 1 factor, there's only 1 number has only 1 factor. That is just number 1. Okay, number 1. And 2 factors. Think about how to make a number have 2 factors. The only possibility is this number is a prime number, right? Prime number. So it will be, we have 2, 3, and 5, and 7. There are 4 choices. And how about 3 factors? How to describe a number with 3 factors? It can only be a prime square, a prime square. P is a prime, P square has 3 factors. Okay. So here we can have 2 square, we can have 3 square, we can have 5 square, but we cannot have 7 square because 7, we only have a single 7 in 10 factorial. We cannot have 7 square. So there are only 3 choices. And totally we have 8. Okay, we have 8 such factors. They have at most 3 factors. Right. This part are on the prime factorization and its properties. So next part, let me talk about something called Lcm and Gcd. That's also an important topic in AMC. LCM means the least common multiple. Okay, for example, we have 2 numbers, A and B. So in general, we could have many numbers. Here, let me just take 2 numbers, A and B. The least common multiple of A and B, we denote by LCM AB. Okay, it's a multiple of A and a multiple of B, but smallest value. GCD means the greatest common divisor of A and B, or greatest common factor of A and B. So the question is how to find LCM and GCD. There are two typical methods required in AMC8. One is called ladder method, and the other is prime factorization. Let me briefly show you how to do ladder method and the prime factorization. So I will take an example. Let's take 120 and say 108. Okay. For simplicity, let me take small number here, but it applies to big number. Ladder method means we just check their common factor. 120 and 108. We see what's the common factor. We start from the smallest prime, right? There's 2. So is 2 a factor? Yes, 2 is a factor for both. So we divide by 2. So we got 60. 108 divided by 2, we got 54. Again, we check 2 again because both of them are even. We can divide by 2 one more time. So I divide by 2. What I have is 30 and 27. Next, we don't have 2 anymore because 27 is odd number. So we should check the next prime number, which is 3. Okay, 3. Let's check 3. Yes, 3 works. If you divide 3, you get 10 and 9. And 9 and 10, they don't share any common divisor larger than 1. So we stop here. So what's the GCD? For GCD of 120 and 108, we basically multiply the numbers on the left. So they are 2, 2, 3. Is 2 times 2 times 3, which is 12. So GCD is 12. And what is LCM? LCM is common multiple. It should be larger. The common multiple, we should multiply not only the left 3 numbers, but also the bottom 2 numbers. Just 2 times 2 times 3, and also the bottom 2 numbers, 10 and 9. So it's equal to 1080. So this kind of method is called ladder method. This picture looks like a ladder. This 2 should be included in the multiplication. Okay. And this idea also applies to 3 numbers. You just apply the same procedure. Next method is based on prime factorization, we just mentioned. So prime factorization, let's factor these 2 numbers. So we can factor 120. It's equals 2q times 3 times 5. And also we get 108. It can be factored into 2 square times 3q. That's all. Okay, that's all. So in this method, we compare their exponents. If you want to find the GCD, we basically take the smaller exponent. Okay, let me show you what it means. So here first, let me match 5 to 108. Because here in 120, we have factors 2, 3, 5. In 108, there's no 5, but just 2 and 3. So we can basically match this 5, but with 0 exponent. Okay, so they have the same format. In this way, we compare their exponent. For 120, the exponents are 3, 1, and 1. For 108, the exponents are 2 and 3, and 0. So the GCD means we take the small exponent for each prime. So we also have 2 and 3 and 5. But when we look at exponent, we take smaller number. For 2, the exponents are 3 and 2. So we take okay, let me write it a little bit. So basically we take a minimum of 3 and minimum of 3 and 2. That's the exponent for 2. And for 3 is the minimum of 1 and 3. For 5, it is the minimum of 1 and 0. So it corresponds to 2 square times 3 and 5 with 0. So this corresponds to 12, right? So the GCD equals 12 here. And if we go to LCM, we do the opposite. We take the maximum exponent. Let me do the computation here. LCM 120, 108. Still we have 2, but here we have a max. We have max of 3 and 2. Max of 1 and 3. Max of 1 and 0. So accordingly, we can write this into 2 cubed times 3 cubed times 5, right? So totally we got 1080. That's the GCD LCM. So this one is based on prime factorization. We compare the exponent. And there's a very interesting fact, that is if you multiply LCM and GCD, that corresponds to the product of A and B. Actually, it's not hard to understand, because if you multiply 2 numbers, you add their exponents, right? And one is smaller number, one is larger number, and it's together. That's equivalent to adding the minimum number and the maximum number. So this is a usual fact. So if we look at the above example, we have that 120 times 108. It's easy to see that equals the GCD 12 times LCM 1080, right? It's easy to see. And it's true for any number, any pair of A and B. So these are typical way to find GCD LCM in AMC8. So next, let me show you some example based on GCD LCM. Here's one. It's from Math Kangaroo. Okay, it says that how many 4-digit number? Let me highlight the keyword. 4-digit number A are there such that half of the number is divisible by 2, and a third of this number is divisible by 3, a fifth of this number is divisible by 5. Okay, let me write down every requirement in mathematics. So first, half of this number is divisible by 2. That means a over 2, this number is divisible by 2. So actually, that corresponds to the original number, a is divisible by 4. I just multiply by 2 both sides, right? And second, if 1/3 of the number is divisible by 3, that means a over 3 is divisible by 3. It says that we have a divisible by 9. Okay, we multiply by 9 by 3 on both sides. Third, we have a over 5 is divisible by 5, right? That corresponds to a is divisible by 25. Now we got all requirements. A is divisible by 4, divisible by 9, and divisible by 25. We conclude that a is divisible by their LCM, and 4, 9, and 25. And actually, this 4, 9, 25, they don't share any common factor. So the LCM just corresponds to their product, which is 900. So our requirement for a is divisible by 900. And also we require a to be a 4-digit number. Okay, let me write this way. Let me write a to be 900 times some number times k. It is a 4-digit number. 4-digit number is at least 1000 and at most 9999. Well, you can divide by 900 on both sides and check the integer part. So k, that implies k is at least 2, but at most 11. Okay, so we see there are totally 10 choices. 10 choices. Okay, the answer here will be 10. Okay, that's LCM. And also, let me do another question related to GCD. Here we go. How many different pairs of positive whole numbers have GCD equals 9 and the LCM equals this 6,930? Okay, here we have both GCD and LCM. Let me write down. So how many pairs? Let me write this pair of number to be A and B. Okay. So we have GCD A and B equals 9. Well, let's do prime factorization for 9, which is 3 squared. Okay, 9. And also we have the LCM of A and B equals 6,930. And I can also do prime factorization. It equals 2 times 3 squared times 5 times 7 times 11. Okay, that's prime factorization. Now A and B, they have GCD equals 3 squared. That means both A and B have 9. So we can have maybe A equals 3 squared times some other parts. Maybe let me call it M. B equals also 3 squared times some other parts. And this M, this N, these two parts will have no more common factor larger than 1. But their LCM also have some other factors like 2, like 5, like 7, like 11. So those two, this prime number, they are from either from M or from N, but not on both. Let me write down each of 2, 5, 7 is either from M or from N, but not both. Because otherwise we have a larger GCD. Okay. So that means 2 will have 2 choices, right? Either it goes to M or goes to N. 3 either goes to M or it goes to N. And 5 you see 5, 7, either from M or from N, and 11, either from M or from N. Each number has two choices where it goes to, right? So totally there are 2 times 2 times 2 times 2 equals 16 cases. Okay, every number has two choices. There are 4 numbers, so 2 times 2 times 2 times 2 times 2. Okay, there are 4 2's multiplied, 16 cases. Okay, 16 cases. But let's read the question more carefully. It says that how many pairs? How many pairs? So for pairs, we just say A and B. The order is not important. It's not important. That means we may have this symmetrical structure, right? A and B and B and A corresponds to the same pair. So A, B, and B, A, these two are the same pair. So among these 16 cases, each case actually repeated twice. So our answer should be 16 divided by 2 equals 8. So there are 8 pairs, 8 pairs. So let's pay attention to the order. If the order matters, sometimes the question asks how many ordered pair A, B. If that's the case, we have 16 cases. If it's just simply pair, the order is not important. We have 8 pairs. So the order matters. Okay, that's for GCD LCM. There's one more topic on number theory. It's called remainder. So at beginning we mentioned that 2 numbers, one divisible by the other. But for many cases, one number is not divisible by the other. If that's the case, we will have something like remainder. We have remainder. So here we study the remainder. We call division with remainder. Okay, a number n divided by little n, not non-zero. There will be a unique quotient q and a remainder r. Here the remainder r is less than this n, the divisor. So okay, for example, I have 2022. If I divide it by, say, 17, I have a quotient equals 118 and plus a remainder 16. So this 118 is the quotient. And this 16 is called remainder. And we see 16 is smaller than 17. Okay, that's division with remainder. In mathematics, we have some notation that's related to this division. It's called Modulo Arithmetics. So here, right here. So if A and B, 2 numbers, both are divided by the same divisor m, they have the same remainder. They will share some similar properties. So we write the following way: A is congruent to B modulo m. That means A and B, they have the same remainder when they are divided by divisor m. Okay. For example, we have like 5 is congruent to 2 when they are divided by 3. Right? 5 divided by 3, we have remainder 2, and this is just 2. Sometimes for convenience, we even use negative number in this notation. I will show you some example later. So here, 5 is congruent to 2. We also have 5 is congruent to -1 mod 3. Okay, because -1 have smaller absolute value, it provides some convenience in computation, right? So here, let me list some main properties shared by the modulo arithmetic. If A is congruent to B modulo m, C is congruent to D modulo m, we can add them and subtract them and multiply them. So A plus or minus A plus C is congruent to B plus D. A minus C is congruent to B minus D. Basically, we just ignore the multiples of m. They don't matter, the remainder. So we just add the remainders or subtract remainders. That corresponds to the same result. Also, we can multiply A times C is congruent to B times D. Okay. Now, a special case is that A times itself, right? A multiplied by itself many times. So we will have A to the k's power. K is an integer, positive integer. If k is a positive integer, a to the kth power is congruent to b to the kth power modulo n under m. So for example, if we consider 5 to the 2022's power, and I want to find the remainder when this is divided by 3. Okay, 5 to the 2022nd power, that's a very big number. So it's hard to see. But we can use this property to simplify quickly. On one hand, we see this 2 to the 2022. But it is true, but it's not easy to see the remainder. So that's why we can use the negative number. That's why we use negative number to simplify. It's congruent to -1, 2022. If you do this way, it's easy to see the answer here is 1 mod 3. So the answer, the remainder is 1 divided by 3. Okay, I will provide you more examples later based on that. First, let me show you a question very typical in AMC8. Here is. So, okay, like we have number 2022. It has a remainder 6 when divided by 7, by 8, and by 9. The question is how many positive integers less than 2022 have the same property. So basically, if you write down, this means 2022 has a remainder 6 mod 7. 2022 has a remainder 6 mod 8. Remainder 6 mod 9. So we like to have the same property for some other number. Let's see this number to be n. N is also has a remainder 6 divided by 7. N has a remainder 6 divided by 8. And remainder 6 divided by 9. Right. How many n less than 2022 satisfy this property? Okay, here these 3 divisors are different. 7, 8, 9, they're different. You cannot combine these. So, but the key is that they have the same remainder. Now they have the same remainder. We can subtract this remainder. So we have n minus 6 corresponds to 0 remainder divided by 7. N minus 6, 0 remainder minus 8. And also n minus 6 has 0 remainder mod 9. Okay, when the remainder equals 0, that means the original, this number is divisible by this 7 is by 8 and by 9. So n minus 6, this is divisible by 7. N minus 6 divisible by 8. N minus 6 divisible by 9. And that corresponds to some question we have done before. So n minus 6 is divisible by the LCM of the 3 numbers, 7, 8, and 9, and it's just multiplying. We got this 504. So n minus 6 is a multiple of 504. So we have n equals 500 plus 4, a multiple. So that's times k and plus 6, right? We require this number to be at most, okay, less than 2022. We can see what kind of k is value. K can be 0, the smallest case is 0, and it can be 1, can be 2, and also 3 words. If k equals 4, that corresponds to 2022. So we consider less than 2022. So there are totally 4 numbers, 4 valued numbers. Yeah, that's all for this question. Now, another question based on remainder. Here we go. What's the last 2 digits of the following big number? 6 to the power 22, a very big number. If you consider the last digit, that's easy because 6 to any exponent is always 6. Last digit is for sure equals 6, right? 6 times 6, 36, or 6, and times 6 again, 6. It's always 6. But here, the question is asking for last 2 digits. So we need to find the 10th digit. Let's pick our 10th digit. Well, here we can write down a couple of terms to see what happens to the last 2 digits. Okay, let's see. we start from the first power, 6 to the first power. This corresponds to just 6. Okay, let me write this way. Let me write 0, 6 here to show last 2 digits. Okay, let me have a remark. So here the last 2 digits is also equivalent to the remainder when it is divided by 100. All right. The last 2 digits is the remainder when the number is divided by 100. So we can write 6 is 0, 6 mod 100. So this is essentially a remainder question. And if you do 6 square, it corresponds to 36. And now we consider 6 cube. Well, we know 6 cube is 216, so we have 16. We can just write 16 mod 100. Now, as the number gets larger and larger, the power of 6 becomes larger and larger. So we don't need to worry about that big number. For example, if we do 6 fours, you don't need to worry about what 6 fours. You just do, it corresponds to 6 cube times 6, right? And 6 cube is congruent to 16. This is congruent to 16 times 6. You just take the last 2 digits of 6 cube and times 6. And then we take the last 2 digits, and that corresponds to 96 mod 100. Okay, and similarly 6 fifths. 6 fifths corresponds to 96. 96 times 6. You don't need to worry about the exact value of 6 to 5. That's a big number. So just do 96 times 6. The last digit corresponds to 76 mod 100. So similarly, 6 to the 6th power, this corresponds to 76 times 6. It is equal to 56 mod 100. Now we write more terms, and we are expecting some repeating pattern. So let's see, 6, 7. If you do 6, 7, that corresponds to 56 times another 6. We get the last 2 digits to be 36. Okay, that's good news because we have 36 before. So the second term shows the last 2 digits to be 36. Here we see 36 again. So by the similar computation, 6 to the 8th power will be 16. The last digit will be 16. And the pattern repeats. So let me highlight. This part is going to repeat. And the repeating. There are 5 terms. So this is okay. I should not include the last part here. Let me redo it. Here, this part. Okay, 5 terms. This is 5 terms. So it repeats every 5 terms. Now our question is to find the last 2 digits for 6 to 2022. Let's see. 2022. Let me first subtract 1 because at the beginning 6 to 1 is not included in this pattern, right? So we should subtract that. So for the remaining part is 2021 divided by 5 is 404 times 5 plus 1 plus 1. So that means this pattern repeats 404 times, and we have additional 1. In the 405th pattern, the cycle, we take the first one. So that implies 6 2022 has the last 2 digits corresponds to the first term in the repeating pattern, 36 mod 100. So the answer here is 36. Okay, you can go find some pattern and see the answer. All right, basically I covered this part for number theory. So it's half time. Let's take a short break. Let's take a 10-minute break. We're gonna resume the class. Next, I will go over counting questions and probability. So let's take a short break now. Okay, everyone, let's come to the second part. Is for counting and the probability. For counting, the first principle is called multiplication principle. It says that we're going to complete a task. This task consists of say several n steps. So step 1, there are A1 different ways to finish step 1. There are A2 different ways to finish step 2. There are A3 different ways to finish step 3. And finally, there are AN different ways to finish step n. The question is the total number of ways to finish the complete task is the product of A1, A2, A3 up to AN. Sometimes a mathematical question could be regarded as a task. If you determine every step, the question is answered. So we will use multiplication principle to count how many value cases there. So I'm going to show you some example. This principle can be illustrated in, let me show a very simple picture. Suppose we have like CD1, we have CD2 and CD3. If I go from CD1 to CD2, suppose there are 2 ways. And from CD2 to CD3, suppose there are 3 ways. Okay, if you want to go to CD1 go from CD1 to CD3, you have to pass CD2, right? So there are 2 ways, there are 3 ways. So the question is, if you want to go from CD1 to CD3, that's the whole task. There are 2 steps, from 1 to 2, step 1, from 2 to 3, step 2. So there are totally 2 times 3, which is 6 ways to go from CD1 to CD3. Okay. There are 2 times 3 equals 6 ways of traveling from 1 to 3. Okay, this is a very simple illustration for the multiplication principle. Now let's do some example based on this principle. Question 1 here. Now we have 4 people, Alice and Betty, and Cindy and Diana. So 4 people, 4 friends. They want to sit on 2 rows of chairs, a front row and a back row. Each row has 3 chairs. Let me draw some picture. Picture helps. So front row, there are 3 chairs. Let me draw 3 boxes. Back row, 3 chairs. Front. This is back. Now, there are some requirement. The requirement is that A and B, Alice and Betty, need to sit next to each other on the same row. This is a requirement. The question is, how many ways can these 4 people be seated among the 6 seats, right? All right, so we can consider the seating as a task. This task is make everybody be seated, right? So we can have the following steps. Step 1, let me seat Alice and Betty. Because there's some special requirement for A and B. So let's consider these 2 persons first. For C and D, they are quite free, so we consider them later. Now for A and B, they need to be seated next to each other. Let's see how many choices we can take to sit like that. We have these 2, Betty, next to each other on the same row, okay, on the same row. Also, we might have these 2 seats. Or we can have, okay, let me just highlight this. Make sure you don't get confused. Last one, okay. So there are totally 4, okay, 4 pairs of seats. 4 pairs of seats. That means A and B, their seats, there are 4 choices. Okay, there are 4 choices. But let's also consider that even though A and B should be next to each other, but there's still some freedom, right? A and B can switch. Okay, A on left or B on left. They can switch. So that corresponds to 4 times 2 equals 8 ways. There are 8 ways to sit A and B. First, we take one pair of 2 seats, right? There are 4 choices. And next, we can switch these two, right? We determine direction. So totally there are 8 ways. You can also consider this switching as another step. But here, let me combine it. Now, once A and B are seated, we consider other people. We have Cindy and Diana, right? Cindy, let's see Cindy. Okay, for example, let me assume A and B are seated here. The occupied is 2C. After that, we have 4 remaining seats. For C, she can sit anywhere. There are 4 choices. Totally free. Four ways. Okay. And after that, we consider D. So once C is seated, okay, there will be 3 remaining seats. So D will have only 3 choices. So after we go through these 3 steps, this task is completed. So we have the answer to be their product. Total number of ways to sit the 4 people will be 8 times 4 times 3, which is 96. There are 96 ways to sit these 4 friends. That's application of multiplication principle. And next, I like to mention some property actually based on multiplication principle. It's called permutation and combination. Let's start from let's do permutation first. Permutation basically means we arrange n distinct items on the row. The total number of ways is n factorial. N factorial is n times n minus 1 times n minus 2 up to 1. There are n factorial ways to arrange n distinct items on the row. It's essentially multiplication principle. We can consider there are n seats, right? Like you have n people, we have n seats. We can label like seat 1, seat 2, seat n. So, and we can seat everybody one by one. So the first person will have n choices. The first person, right? And the second person will have n minus 1 choices because the first person occupied 1 seat, there are n minus 1 remaining seat. And similarly, the third person has n minus 2 choices. The fourth person always has n minus 3. And the last person have just 1 seat remaining. So the last one. So that's why we have n factorial. This is a permutation. It's from multiplication principle. Now let's do an example based on this permutation. How many numbers less than 10,000 have the product of their digits equal to 126? Okay, basically we have some number, there are a couple of digits. We multiply these digits, the product equals 126. How many numbers are less than 10,000? Okay, in order to solve this question, let's see what are possible digits. These digits must be factors or divisors of 126. So let's do prime factorization to get a possible divisor. So 126, we do prime factorization equals 2 times 3 squared times 7. Okay, you can double check. So that's 126. Now we can check that this number cannot be too small. Say this number cannot be single digit, right? Of course, the number cannot be 1 digit. It cannot be 2 digit. If it's 2 digit, you know, the largest possible product is 9 times 9, which is 81, but it's still smaller than 126. So it cannot be 2 digit. But it is possible to be 3 digits. Let's see. So let's consider 3 digit. It's at most 4 digit, right? So because less than 10,000, at most 4 digit. So we just discussed these 2 cases, 4 digit case or 3 digit case. Now let's see 3 digit case. Because number cannot be 2 digit, right? So in 3 digit case, we cannot have digit 1. If you have digit 1, that's essentially 2 digit case. So we consider the product of 126 into three numbers. There are basically two cases. First, we know that 7 cannot be multiplied by 2 or 3, otherwise it's bigger than 9. So 7 should be isolated. And the 2 and the 3, they could be multiplied or separated. Let's consider two cases. 2 times 3 squared, which is 9, and 7. This is one way. And this is another way, 2 and 3 combined. So 6 times 3 and times 7. This is another case, okay? We don't have more. We don't have more. Now, for 3 digits, using 2, 9, and 7, we just do permutation. So that means how many ways we can arrange these 3 digits to get different numbers. That corresponds to 3 factorial, which is 6. There are 6 numbers. Similarly, for 6, 3, and 7, still we have 3 distinct digits. So again, 3 factorial, which is 6. So next, let's consider 4-digit case. For 4-digit case, it's possible. It's okay if we have a 1 included. So if you have 1, that's essentially the previous 3-digit case. So 1 times like 2, 9, and 7, or you have 1 times 6 and 3 and 7. And we may also have the case that 1 is not included. If 1 is not included, you see 126 2 times 3 squared times 7, we can have at most 4 terms larger than 1 multiplied. So that corresponds to 2 times 3 times 3 times 7. Right. So for 1, 2, 9, 7, this is 4 factorial. We have 4 factorial equals 24 cases. For 1, 6, 3, 7, again, there are 4 distinct digits. We have 4 factorial, that is 24. But for 2, 3, 3, 7, let's be careful, because here we have 2 digits the same. We have 2 3s. 3 is repeated. And we cannot just do 4 factorial because 3 repeated. If we do factorial, 4 factorial, we have repeated terms. That means if these 2 3 are switched, that corresponds to the same number. In that sense, we need to divide 4 factorial by 2. So the number of different terms is 12. So those are 5 cases, and then we add them together. They are totally 72 cases. So the answer to this question is 72. Okay, this is a permutation. Okay, sometimes we need some case work. Next, let me share the combination. In permutation, we know the order matters, but in combination, it's like we have n items, and we select k items from n items. How many ways can we do that? It's called n choose k. This is notation, n choose k. That's n factorial divided by k factorial divided by n minus k factorial. Or if you want, you can simplify it into n minus k plus 1, n minus k plus 2, all the way up to n, and divide by k factorial. That's equivalent. And for example, we have 5 choose 2 equals like 5 factorial divided by 2 factorial and 3 factorial. The reason is because 5 factorial divided by 3 factorial, you have only 3 and 4 and 5 remain. So this is 4 times 5 divided by 2, which is 10. Now, a very useful fact is that n choose k. This is equivalent to have n. We don't choose n minus k. So n choose k is equivalent to n choose n minus k. Okay. So for example, 5 choose 2 is equivalent to 5 choose 3. 5 choose 3 is 5 factorial. You have 3 factorial, 2 factorial. Usually that's the same. It's also true for any n k. Okay. Here n is largely equal to k. So here we have an example. The question is that we have numbers from 1 to 17, positive integers. In how many ways we can select 3? We select 3 distinct integers, and they form a arithmetic sequence. For an arithmetic sequence. In some order, we can rearrange to make an arithmetic sequence. In how many ways? Okay, let me first show you a way that many people will do. That's somebody will do case work. For example, we have A and B and C. When we see arithmetic sequence from A to B, there's common difference, right? Let me arrange in increasing order. B from B to C, this difference D, this difference D, right? Let's go D is common difference. Well, for different arithmetic sequence, we can discuss different common difference. For example, this D, we can, because they are distinct numbers, right? So D should be at least 1. Suppose D equals 1. Well, you can discuss like 1, 2, 3. That's a case, right? And also 2, 3, 4. That's a case. And you just discuss all cases up to 15, 16, and 17, right? And we see there are 15 cases, right? 15 cases. And if you discuss D equals 2, you will have, it will start from the smallest one, 1, 3, and 5, and 2, 4, and 6, and so on, up to 13, 15, and 17, right? So this corresponds to 13. Oh, sorry, so, yeah, 13 cases. Because you just check the beginning number, okay? And similarly, you can discuss D equals 3, 1, 4, 7, 2, 5, and 8, okay, and up to finally 11, 14, and 17. Okay, this we have 11 cases, and actually you can find some pattern. Finally, let's consider what's the largest common difference. The largest common difference could be 8, because it's 1, 9, and 17. There's only one term. This is 1. I think this is case 8, right? Case 8. So here are some terms I missed. So totally we just add these numbers, right? That's the answer. 1 plus 2. Okay, every term is odd number, starting from 1 plus 3 plus 5 up to 15. All odd numbers. Here we have how many terms? We have 8 terms. This is a fact, very useful fact. The first k odd numbers add up to k squared. So here we have 8 terms. 8 terms, the sum is basically 8 squared. 64. Okay, 64 is the answer. So this is a method. We don't use any math techniques. We just do this discussion, do case work. However, as we learn this combination, this is a very simple way. Let me introduce that to you. So when we consider this arithmetic sequence, a fact is that the middle number is the average of the first number or the last number. That describes the arithmetic sequence of 3 terms. So in this way, we have all of them to be integer, right? To be whole number, integer. That means A plus C must be even number. Otherwise, we don't have B to be integer, right? So A plus C should be even number. How to make A plus C to be even number? We have either A, C both odd or both even. Both A and C are odd, or both A and C are even. You can check any case, any value case. Now we just need to select 2 odd numbers or 2 even numbers, and B is automatically determined. So from 1 to 17, we have 9 odd numbers. There are 9 odd numbers, and also 8 even numbers. So we can do the computation. If we want to find 2 odd numbers, basically we do 9 choose 2. That's the first case. If you want to find 2 even numbers, you just do 8 choose 2. And I just apply the formula. You will see this is 36 plus 28. You got 64. So if you know this combination techniques, you can solve the question very quickly. In AMC8, we have very limited time, so it's very important to find a fast way. So let's do this combination method. So next technique I want to introduce is called inclusion exclusion principle. Maybe you heard about it before. There are 2 cases. Let me do the 2 set case first. Here A and B are two sets, and they may have some overlap. So we consider A and B include some numbers, some elements, some objects. We like to count totally how many objects are included. So here the notation is called A union B. A union B means totally how many the union set. Here I put absolute value, means that how many numbers, how many objects in this set. Okay. It says that A union B equals A plus B, the number in A, the number in B minus their intersection, because this union is equal to this A and plus this B, but we subtract this intersection because intersection is counted twice. Let's subtract it. That's why we have the inclusion exclusion principle. So A plus B, that's called inclusion, minus that means exclusion. Inclusion exclusion principle. Right? Now let's just apply it and do some computation. How many integers between 1 and 22 are divisible by 20 or divisible by 22? Okay, so here we have two sets, right? One set of numbers are divisible by 20. The other set of numbers are divisible by 22. So we use two set inclusion exclusion principle. So let's denote A, the numbers divisible by 20, and B, let me write this way, B, the numbers divisible by 22. Okay, in the computation, we also need A intersect B. So A intersect B, that means the numbers divisible by both 20 and 22. By both 20 and 22. And that corresponds to numbers divisible by their least common multiple, LCM. We just learned LCM. And you check LCM here is 220. Now let's do computation. First, let's count how many numbers in A. Numbers divisible by 20. From 1 to 22, we basically do 22 divided by 20, right? What's the largest multiple of 20 here? But this is not an integer. So we take the integer part. Here we have a notation called floor function. We take the integer part. And this number, if you calculate, it's a little bit larger than 101, but smaller than 102. So it's 101 point something. And so we take the integer part. Here is 101. Okay. That's the number of numbers in A. And second, we do B, 22 divided by 22. Similarly, we take the integer part, floor function applied. It corresponds to 91. Okay, it's 91 point something, smaller than 92. Finally, we have 22 divided by 220. Take the integer part, it's equal to 9, I think. So finally, we see A union B. A union B is equal to 101 plus 91 minus 9, which is 191. Okay, so that's the answer. We have 191 numbers between 1 to 22 divisible by 20 or 22. Okay, sometimes the question asks you the opposite. Sometimes, say, for example, it asks how many numbers are not, okay, it's used by neither 20 or 22, not divisible. So you just subtract 191 from 2022. Okay, that's a similar question. Next, let's also consider the inclusion exclusion principle for 3 sets. Here we show the picture. It's much more complicated. We have 3 sets. We'd like to find the total number of elements covered by the 3 sets because they overlap. So we have 3 types of sets. One is the single set. Here's the formula. Let me rewrite it. So we like to find A union B union C, the total numbers. It corresponds to, first we add the numbers from each set, A plus B plus C. Next, we minus the intersection of two sets. We minus, okay, let me put into parentheses. We have A intersect B, B intersect C, C intersect A. This part, we subtract it. And finally, we add back the intersection of all three sets. Okay. Here, actually, we have very nice, it looks complicated, but we have very nice pattern. The first row here is positive, right? Positive. We add all this single set. Second one, we have a negative. Third one, we have a positive again. So this is always true in inclusion exclusion principle, plus, minus, plus, okay? So it's not too hard to memorize that. Plus single set, minus two set intersection, plus back three set intersection. So actually they are more complicated in inclusion exclusion principle, like 4 set, 5 set, but always following the same pattern. So this is the formula. All right, here's one example. Let me give you example. Okay, Jason, a student, takes a survey of his 30 classmates. He gets the following result. Okay, what class they like? Okay, 16 people like literature class, and 21 like science class, and 18 like math class, and 15 like literature and science, 9 like science and math, 7 like math and literature. Now the question is how many students like all 3 classes, literature, science, and math? Okay, see, we have 3 categories, right? So we just denote by 3 sets. The people like literature class, we denote by A. And so we have A, they are 16, right? The people like the science class, we call it B and C. So B, we have 21. C, we have 18. Now, people like literature and science, that's the intersection of A and B. And it says A and there are 15 such students. And then people like science and math, that's B and C intersect, right? So we have 9 students. C, math and literature, so C intersect A. We have 7 students. Now the question is to find how many people in all 3 sets. That's the question, right? So what we do is just apply inclusion exclusion principle. We know, okay, let me just write down A union B union C. A union B union C means all classmates. It says there we have 30 students, right? 30 students in the survey, okay? In the survey. So it includes A, 16, B, 21, 18. Now I always subtract the intersection of 2 sets. Subtract 15, subtract 9, subtract 7. And then finally I need to plus the intersection of all 3. And now we already have an equation. We just do computation. You see, this is only unknown. It can be solved to be 6. So there are 6 students like all 3 classes. That's application of inclusion exclusion principle of 3 sets. Right. So next, let me introduce a typical technique in counting called binding. The other one is called insertion. Binding, by the name we know, is just to combine some terms together, consider together, and that's very natural. Let's see this example. So okay, so let me take 7 people. Okay, A B C D E F G, 7 people. They stand in a row to take a photo. In harmonic arrangement, we have the following 2 requirements satisfied. The first requirement is that A and B should stand next to each other. And second one is C and D should stand next to each other. So if there's no requirement, we have 7 people. Basically, the answer is 7 factorial, the permutation, right? But here we should consider these 2 requirements. Because A and B should stand next to each other, that means they are kind of combined. They're together, okay? So we put them together. Let me put A and B to be a set. They cannot be separate, so let's put A, B together. C and D similarly should be together. Now, For other three people, they are totally free. They can stand anywhere. E, F, G, no requirement. Now let's see. Because A, B are binding, C are kind of binding, so we can consider this to be five groups of people. Let me call it 5 people. Okay, 5 people. The first two groups have 2 people. Now we can arrange these 5 people first. Let's say step 1. Arrange this 5 people. 5 groups, actually, 5 groups. That corresponds to 5 factorial, which is 120. It's not hard to find it. And next, A and B, they are binded together, but we still have some freedom. A, B can switch, right? Which person on the left, which person on the right, we can switch. So there are two choices. There's some freedom. So A, B can switch. So there are 2 ways. Step 3, CD can also switch. That corresponds to 2. So let's apply multiplication principle again. If we go through these 3 steps, arrangement is determined. So by multiplication principle, the answer equals 5 factorial times 2, and it gives 480. So there are 480 valid arrangement. That's our binding. Okay, here I'm showing binding A, B together, C together. They are considered as a group, a special people. Okay, this is binding, very natural. Next one, let me show you a technique called insertion. It's also very powerful, and it appears in AMC8 in recent years. So let me show you the first question. Now, one person, Alex, has 15 identical marbles. In how many ways can he share these marbles with his friend, okay, Ben, Charlie, and Daniel? So everyone of these 4 people has at least 1 marble. So here I like to highlight some keywords. The keywords here are everybody has at least 1 marble. The other keyword is that those marbles are identical. Those 2 are keywords. Because they are all identical, what matters is the number only. We don't distinguish marbles, so what matters is just the number at everybody's hand. So let me call the numbers to be A, B, C, D. Alex has A. Okay, Alex, A marbles. And the Ben, let's see, we have B marbles, and the Charlie. We have a C marbles, and the Daniel. We have a D marbles, right? We have a totally 15 marbles. That corresponds to the sum, A plus B plus C plus D. The sum must be equal to 15. And on the other hand, everybody should have at least 1 marble. That means these 4 numbers are at least 1. This question can be viewed as dividing 15 into 4 groups. So let me roughly draw a picture. Now I'm drawing 15 marbles. Should be divided into 4 groups. Everybody has at least 1 marble. So to divide into 4 groups is equivalent to insert some separator. I can insert some separator between these marbles. I cannot put separator outside because everybody has at least 1 marble. So there are 15 marbles. That corresponds to 14 places. There are 14 places to put separator, and we need to put into we need to divide into 4 groups. We need 3 separators. For example, I take 1 separator here, maybe 1 here, maybe 1 here. I put 3 separators or divider separator, right? So the question is just 14, choose 3. 14 choose 3, you just do computation 14 divided by 14 factorial divided by 3 factorial, 11 factorial. Finally, you got 364. There are 364 ways to distribute this marble. This kind of idea is called insertion. Sometimes maybe you call it stick bar, whatever name, but that means the same thing. Okay, 14 choose 3. And this question, we can do similar thing for some modification. Let me modify a little bit. Now, what if everybody has at least 3 marbles? So the formula is the same, right? A, B, C, D is still 15, but the only requirement is change is A, B, C, D, or at least 3. That's the change in the requirement. And we can do the similar argument. Well, here we do some transformation. Let me modify a little bit to transfer to the previous question. What I do is that because I have 3, I'm going to subtract 2 in order to make let me subtract 2 from A, B, C, D to get some number larger equal to 1. So if A minus 2, let me denote by X. B minus 2, let me call this Y. C minus 2, let me call it to be Z. D minus 2, let me call it to be W. Right? So basically, let me repeat. Okay, A minus 2, B minus 2 is Y, Z is C minus 2, and W is D minus 2. Okay. In this way, X plus Y plus Z plus W equals 15 minus 8, which is 7. And still we have a similar requirement, X, Y, Z, W larger equal to 1. That's basically the same question, but change the number. It's equivalent to divide 7 marbles into 4 groups. Again, 7 marbles implies 6 places to insert a separator, right? 6 places. And then we need to divide into 4 groups. We need 3 separators. 3 separators. So it's basically, 6 choose 3, 20. The answer becomes 20. And of course, you can change the data. Like Alex has at least 1 marble, Ben has at least 2 marbles, and Charlie 3 marbles, Daniel maybe 4 marbles, like that. You can change and do a similar argument. You will solve the answer. Okay, and that's the question here. Right, that's basically typical techniques in AMC8 counting. Next, let me briefly mention probability. For probability, let me just record the concept first. There are basically 2 types of probability. One is discrete case, one is a continuous case. For discrete case, it's almost like a counting question. Because, okay, if you record the definition probability, we have, okay, we perform certain experiments, we perform certain operation. There are different possible outcomes. Here, discrete case, we have finite cases, finite scenarios. If you collect all outcomes, this set we call it sample space. All possible outcomes together get sample space. And sometimes we consider probability of certain event happens. Certain event corresponds to a subset of these outcomes. So here, let me call it E, right? The valid cases, you can call it. So the probability, okay, here we assume every outcome are equally likely. They're equally likely. In this case, the probability equals the number of outcomes in E divided by the number of outcomes in X. So basically, absolute value E divided by absolute value S. So yeah, it's basically a counting question because each part of E and S, they could be calculated by counting techniques. But sometimes it's related to number theory or maybe some other mathematical topics, like sequence, like some other problem. But essentially, it's counting question. Okay, let's see some example. Typical problems are related to flipping coins or through dice. Here, let me do one question. 2 dice are thrown at random. Okay, let me say 2 normal die. For a normal die, that is the number from 1 to 6, okay? It's thrown random. Okay, find the probability that this 2 number these two numbers obtained are the two digits of a perfect square. Of a perfect square. So let me call it die 1. So at die 1, we have 6 outcomes. 1, 2, 3, 4, 5, 6, right? Die 2, similarly. 1, 2, 3, 4, 5, 6. So the outcome is D1 and D2. D1 has 6 choices, D2 has 6 choices. Totally, we calculate the total number in the sample space, total number of possible outcomes. It will be 6 times 6. It's a multiplication principle again. Die 1 has 6 choices, die 2 has 6 choices. Totally, we have 36 outcomes. That's the sample space. Here we need to consider the valid case, okay? Here we consider the case that these two numbers are 2 digits of a perfect square. Now let's discuss what could be the perfect square. Okay, it's at least 10, okay, and every number is at least 1. So we have 16, right? The smallest perfect square up to 10 is 16. 16 corresponds to 1, 6. And accordingly, we can also have 6, 1, right? Because we can reorder it. And next, we consider 2, 20 something. Okay, 25 is a perfect square. So 2, 5. And we can switch 5, 2, also make this perfect square. For 3, we have 36. So 3, 6. And also 6, 3. 4, okay, 49. Okay, 49 is not good because 9 is not possible. And 50 something, there's no perfect square. 60, 64 is a perfect square. So we can have 64 or 46. Okay, we list all cases, right? So this is the set E. Now we can easily see that there are 8. There are 8 cases in the set E. So the probability here is just the division, the quotient of these two numbers, which is valid numbers 8, or numbers 36, which is 2 over 9. And that's the answer. Okay, next, let me also do a question that's related to number theory, okay? Number theory. Yeah. Now we have digits 2, 3, 4, 5, 6. They are randomly arranged. Okay, we have permutation here, 5 numbers, to make a 5-digit number. What's the probability that this number is divisible by 22? So it seems to be a number theory question, but in terms of probability. Okay, let's see. Well, first we consider the sample space. Sample space is all arrangement. Because these are 5 distinct digits. We got that this is basically 5 factorial, which is 120. So there are 120 different 5-digit numbers. Okay, some of them are divisible by 22, some are not. So let's see how many of them are divisible by 22. Let's consider E. Well, a number to be divisible by 22, we note that 22 equals 2 times 11. So this number, okay, let me give a notation. The number n such that n is divisible by 22. Okay, n is divisible by 22. That implies n is divisible by 2, and at the same time, n is divisible by 11. Right. So n is divisible by 2. That's easy. We just require the last digit to be even. That's not too hard. Now, n is divisible by 11. We record the divisibility test for 11. That's alternating sum, divisible by 11. Okay, let me draw 5 boxes to denote these 5 digits. And okay, let me call A, B, C, D, E. Okay, in any permutation, we know the sum of digits equals this 5 digit, right? 5 numbers, the sum 5 numbers. It is 2, 3, 4, 5, and the 6. We know it's 20. So the sum is always 20. But here we split this into 2 groups, right? And do subtraction. This is even places. So we should have A plus C plus E minus b plus d. This number should be divisible by 11. But their sum, okay, here let me call this two numbers. Let me call x, y. So we know x plus y equals 20, but x minus y equals is a multiple of 11. What's possible here? So x minus y, the total sum is 20. So we cannot have like 22 or minus 22. X minus y could be minus 11 or 0 or 11, right? But however, we know x plus y equals 20. You know, x plus y and x minus y, they have the same parity. I mentioned before, okay? I mentioned before. So this must be even because x plus y is even, 20 is even. That implies x minus y is also even. So that implies x minus y should be 0. Okay. Now we can solve x and y. Implies x equals y equals 10. In other words, a plus c plus e equals 10, and b plus d equals 10. All right, let's see what's possible combination. B plus d, two numbers add up to 10. We have only one case, that is 4 and 6. We don't have other choice. You can easily check. So we must have in B and D, it is 4 and 6. In A, C, E, that is 2, 3, and 5. Now let's see how many possible cases there. First, let's recall this number should be even, right? Should be even. So the last digit should be even. And the last digit are from 2, 3, 5. So last digit must be 2. And 3 and 5 goes to here. And 6 and 4 goes to here. So 3 and 5, there are 2 choices. 6 and 4, there are also 2 choices. Totally, we have four ways. So that means we have 4 valid numbers that are divisible by 22. So we have E equals 4. And the probability equals 4 divided by 120, because 120 is the total number of permutation. 120, which is 1 over 30. Okay, that's the answer here. Okay, that's discrete probability. So finally, let me also briefly mention continuous. Okay, there's one more question. Let me quickly do it. Yeah. Okay, another question is randomly pick 2 edges from a cube. What is the probability that they are parallel? Okay, I'm putting this question here to show some tips in doing AMC8 question. So for a cube, there are 12 edges, right? We randomly pick 2 edges. So that's the total sample space. Okay, sample space, we have basically 12 choose 2. 12 choose 2, that's total number of ways to pick 2 edges, 66. Now we consider the valid choice. That is 2 edges, they are parallel. Now parallel means these edges pointing in the same direction. Let's see. Here we have basically 3 directions, right? Yeah, 3 directions in 3D. So for example, these 4 edges are parallel. And there are 2 other directions. Among these 3 red lines, I can have a valid choice, 4 choose 2, right? Also, let me find another, this green. For green edges, we can also provide some valid choices, 4 choose 2. And then finally, we have the blue. For blue lines, again, 4 choose 2. This corresponds to the valid cases, valid choices. So that's 6 plus 6 plus 6, which equals 18. 18, okay? And now what is the probability? That's the division of this 2 number, which is 18 divided by 66, which is 3 divided by 11, okay? This is the normal way to do it. But here, let me also mention another technique in AMC8 that's useful. It's called using symmetry. Using symmetry. If you use symmetry, the question can be solved very quickly. Let me also draw the cube here. because this cube is very symmetrical, we can fix one edge. You can fix any edge, the discussion will be the same. Let's fix one edge. And then we consider the possibility for the other edge. For the second edge, from the remaining 11 edges, right? There are 11 choices. And let's see how many of them are parallel to this red line. We know 3 of them are valid. So the probability is basically 3 divided by 11. Here, you don't need to do complicated computation using permutation combination. By symmetry, you can solve this quickly. It's applied only to this symmetrical structure. Okay, I just introduced that to you. All right. Finally, let me briefly mention probability in the continuous case. The idea is similar, but here we would have the sample space to be a continuous set, and there are basically infinite many points. In the discrete case, there are only finite scenarios, so we can just count. Here in continuous case, we have infinite many cases. So the collection of all outcomes will make a continuous set. Sometimes it's like a 1D case. All possible outcomes corresponds to a line segment. And the valid case, the valid outcome corresponds to some other set. The probability corresponds to the ratio of their length. Here we consider the length. This is 1D. And if it's 2D, we will consider the area, 3D, the volume. So in AMC8, we have basically just 1D or 2D. We don't have 3D. Actually, there are not too many continuous probability in AMC8. So if it's 2D, let me just S, and E, some set, this is E. So the probability is the area of E divided by the area of S. Okay? That's continuous case. And here also we require every point, every outcome equally likely to appear. Okay? So here, let me give you one example. Now we have a dartboard. It's a circle. The outer circle has a radius 2, and the inner circle has a radius 1. We have 2 perpendicular diameters. Divide this into 4 congruent regions for each circle. Now, every region, there's a point. There's a value here. The probability that a dart will hit a given region is proportional to the area of that region. Now, we have 2 dots hit on this board. The score will be the product of these 2 values. Now, the question is, what's the probability that this score is positive? Okay, see, we have a positive number, negative number. If the product is positive, we should have positive times positive or negative times negative. So let's first figure out the probability of getting a positive number and the probability of getting a negative number. That corresponds to calculating, the area. So we have a total area, that is S, the big circle. This radius is 2, so we get pi times r square, which is 4 pi. And now for inner circle, small circle, that is pi. Okay, pi times 1 square is pi, but it is split into 4 parts. So each part corresponds to pi over 4. So here's also pi over 4, pi over 4, pi over 4. Okay, and for the outer part, the annulus, we have 3 pi. Okay, totally 4 pi. Subtract 1 pi, we have 3 pi. Divided into 4 parts. So that's 3 pi divided by 4, 3 pi divided by 4, 3 pi divided by 4. Again, 3 pi divided by 4. Now, let's see the area corresponds to, let's see, 1. 1, we have area here and also here. We would write to probability of getting 1. Probability of getting 1 is the area corresponds to 1. We have pi over 4 plus 3 pi over 4 times 3 divided by the total area, which is 4 pi. This probability equals 5 over 8. 5 over 8. Okay. And similarly, you can get a probability of getting -1. Well, it's just 1 minus, right, 5 over 8, or you can do the computation like that. But here I'm just subtract this from 1, it corresponds to 3 over 8. Right, finally, we can do the computation to get a product to be positive. Well, we have positive times positive, right? Positive, positive. That corresponds 5/8 times 5/8, which is 25/64. If both are negative, negative times negative, that corresponds 3/8 times 3/8, which is 9/64. And now you can add them together, which you get 34/64, which is 17/32. So our answer is 17/32. This is an example of a continuous probability. Okay. All right, I think time's up. I need to stop here, and I give you brief this introduction for these three topics. There are some more details I cannot cover. I'm suggesting you to read our textbook. Okay, it's written by Morningstar Institute. It's totally free, available online. I'm showing here the link. And also you can just Google Morningstar Institute textbook. You will find this book, Level A. Okay, Level A is for AMC8. You can read these chapters and prepare for your coming AMC8 test.